Alright guys, so we are looking at Simon's algorithm. Yeah, that's right. We're looking at Simon's algorithm. Now, to understand Simon's algorithm, we first have to understand Simon's problem. So Simon's problem is that we have some function which is unknown to us besides the properties that it takes a bit string of length n and it outputs a bit string of length n. Now it has this unique property that it is a 2-to-1 map, meaning that for every value of x that Simon's problem takes, there is it outputs the same value for a different bit string for every x, where the reason it's 2-to-1 is because there's this unique, I forgot, I think this was called a mask in the literature, the notes from the course, or it might have been key, I'm not sure, but basically this s, meaning that the function taking some input x outputs the same value for x modulo 2, summed together bitwise with this mask, and it does this for um, every possible x value. Now, when I first heard about this, there was a misunderstanding that I personally made, and I want to make it clear so you guys don't make the same mistake. Do not misunderstand this in the sense that x is the same as x summed together bitwise with this mask or key. This is not the case. There's a difference. It's because the 2-to-1 mapping happens because of the function, not the mask itself for the bit. A neat illustration I found is like this, which is that for every value that f outputs, there are two possible values they can contribute to this output, those being x and x with the mask. And this happens for like every possible pair. But it's the same S. It's just a single mask. And Simon's problem says, you know, what is this mask? Now, the fastest, or like, sorry, the worst case scenario for calculating what the mask is in a classical sense is half plus 1, which is 2 to the n minus 1 plus 1. Um, Now, Simon's algorithm in the quantum case is actually an exponential speedup. I think this was actually the first exponential speedup we found using quantum computers. So this was like the first like real big thing, if I'm not mistaken. Now this is what Simon's algorithm looks like. We have two sets of registers of 0 qubits. We have a set of n and a set of n. And this actually corresponds to this expression up here, which basically just said that we have our input and we have our output, and they are both of the same length, which is why we need one for the result and one for the calculation. Now, the stages are that for the first register, we apply Hadamard. We then use our function on the second register and then measure the second register to collapse the system, after which we Hadamard the first system and get a set of linear equations, but I'm going to come back to why this is later. So far, let's just look at what actually happens step by step during the algorithm. Now, for simplicity, I didn't bother writing the normalization. Like, you can keep track of it. Like, if you know how many qubits there are, you know what the normalization is. So, with that being said, we start out in this state right here, which obviously just corresponds to 2n qubits tensored together, like this, after which we apply a Hadamard transformation to every qubit from the first register. This obviously sends our system into a superposition for the first qubits, an equal superposition of every possible bit string. We've seen this before a million times so far. Well, maybe you guys haven't, but you know, you've seen it before at least. Now, we then use this as an input to calculate the function f and apply it or sort of express this register as the result of that, basically we're taking this as an input and producing this output on the second register, which is the one down here. And that's what this unitary transformation does right here. It just calculates the function f. And obviously, that just puts us into this scenario right here, where x or the first register is just the equal superposition, and then the second register is just the function to that x. Cool. Now, what we measure down here, we measure the second register, which collapses the function into one of the values. So and from this illustration, this would be the same as measuring in this domain, and hypothetically, let's just say it collapsed to this point right here. Let's say that this point we call A. Then this would correspond to the second register down here, collapsing to that specific result, f of A. Now that would obviously have the inverse effect of corresponding to our input register being, or sort of like being whatever would result in this. Basically, if we measured that the second register was f of A, that would only be possible if our input register was like either one input or the other, that of the ones that would contribute to this, obviously. Now the only two possibilities, because it's 2 to 1, are just x or x with the mask. But for this specific scenario, we're just calling this specific result A. So cool, we're in this situation. Now there's really just two steps left to do, which is that after we've measured and collapsed both registers, and our first register up here is in a superposition, we then Hadamard this register up here. From Hadamarding the first register, we get this expression right here. Now, I'm not going to justify how we get to this, because to be honest, it's just like something you have to look up online, or like it should be quote unquote demonstrated or proven in your notes, because I myself didn't feel like reading a wall of text to understand how we got from this point to this point right here. But without needing to understand it, we can still get away with just knowing how this current equation works. So if we focus on this expression right here, we have the number 1 plus -1 to the power of s dotted with y, which is the second register. My bad, no, not the second register. I forgot to write out y. Um, Now, y is sort of the sort of code we're looking for, but I want you to notice this. So for this entire expression right here, what are the possible values we can get? Well, because we're dotting bit strings of equal length, that means we can either get the value 0 or 1. If the result is 1, then this entire expression will be 1 minus 1, which is 0, meaning that this amplitude right here, if s dotted with y is 0, or sorry, is 1, it would always result in the amplitude being 0, and thus we would never measure this state. The only other option is that if the mask, sort of dotted with the code, is equal to 1. In that case, it becomes 2 sort of divided by 2, because I didn't bother to write out the normalization, but the sort of amplitude for this specific ket would become 1, and so we would all, in other words, what I'm saying is when we would measure and then perform a Hadamard, the only possible states available are not the cases where we have our specific mask, but only the cases where I have our code with the mask like this. What does this practically mean for us? Well, it means that if we run the algorithm several times, which I mean just like, some amount of time, let's just say k, we would get a set of linear equations which one can solve. Now, the thing about this set of linear equations is that the amount needed to solve it is scales linearly, but the classical computational requirement to solve the system would be exponential, meaning that because we're going from an exponential requirement to a linear requirement, we get an exponential speed up, which is why Simon's algorithm is so powerful. Um, but yeah, once you solve this set of linear equations, this is what I meant by we only get, the masked equations. You never get y1 itself. You only get like y1 dotted with s, y2 dotted with s, etc. Once you have your set of linear equations, you just solve for s to get the mask, which results in this exponential speed up. I hope this made sense, and yeah, take care. Thanks for watching.